about reconstruction of the wave speed in geophysical inverse problem and inverse problems or inverse problem of the sphere data. So it's also related to applications, which I think is the goal of this conference, right? So Mark, please.
Yeah, so thank you very much. This morning I was thanking for the organizers for the invitation on behalf of Günther Ullmann, and now I would like to just myself to thank and give this talk that I plan to give here. So from the space-time, let's return back to the Earth and consider a geophysical inverse problem. You could also think this from the geometrical point of view, and then the title would be alternative. The title would be an inverse problem for sphere data. And this work has been done in collaboration with Martin de Hoop from Purdue, Sean Holman, who is now at Manchester, and two Norwegian geophysicists, Einar Iversen and Björn Ursin. So I will first discuss some geophysical measurements. Then the abstraction of this type of measurements corresponds sphere data, like the surfaces of spheres. And the idea will be that this inverse problem can be solved in a quite constructive manner by solving ordinary differential equations on a curve. So let us consider two geophysical inverse problems. One is that this may be more standard one, that one would have varying wave speed here, and there are discontinuities that cause reflections. Other possibility would be to consider model where you have lots of point scatterers, that the wave speed would vary here, and you would have lots of point scatterers. Geophysicists have this type of like practical signal processing tools to approximate data to move from this model to this model and vice versa. You could think that all these surfaces here you would replace by sequences of points, and then the data would be much more closer. So this is maybe more from how commonly studied problem, and this is but this is the problem that we studied today. And often also in this type of problems one assumes that one knows some smooth background wave speed and want to reconstruct it, want to reconstruct the locations of these surfaces or these point scatterers. And in this talk we assume that the unknown velocity, that the velocity here in the medium is unknown, and there are lots of scattering, and we are considering single scattering this type of measurements from this type of domain. So let's just consider these kind of typical geophysical pictures. So one could think this way, that so here is surface of the Earth, and here is depth. So here is x, and here is depth z. And let's put here a point scatterer and consider the measurement. One sends a signal from here. This is a homogeneous space, so it propagates, reflects, and comes back. And then in the measurement picture, here would be this x variable, and here would be t, the measurement time, and I'm considering zero offset data. So the receiver and the source are at the same point. So at this point, that is at receiver, that is actually at this location, waves travel from surface to the scatter, reflect, and come back. So here would be twice this time. At this point, waves would travel like in this way, come back. One would have this type of point. The reflection is recorded at this time. Here it looks like this, comes from here, and here you have a parabolic curve that corresponds to a point scatter. So this corresponds to offset zero data. So source and receivers are at the same point. So in the measurement data, this type of curve corresponds to point scatter. Now one could consider this is the simulation. In a toy case, you would have a slightly varying wave speed, and you would have this type of measurement data. So this picture would correspond to this data here, and you can see that probably that there are point scatterers here and there, quite many of them, and you would ask that what is the wave speed in the medium? How you could do that? And the idea of this problem was that geophysicists say that, okay, that from the geophysical data, by using image processing, one can see this type of wavefronts and measure how curved they are. So how this type of data could be used to find the wave speed. So let's now consider this type of data. And instead of doing measurements on the boundary, so on the surface of the Earth, let's continue the Earth on top of this in the way that so when here is the surface of the Earth, here is some point here, I extend Earth as homogeneous medium on top of the Earth, and at this point we could then consider what's the travel time from here to here. By using our data, we could somehow consider that, okay, travel time from here to here is some number, and then we add the travel time that we can compute here, simulating data, and then we would consider all these type of combinations and take the minimum. In this way, we could get the travel time from this point scatter P to measurement point X here. So we actually extend the data on top of the Earth in this manner. So here is just this kind of like extension of the distance function from the boundary to the space above. And now it's time to somehow look this type of data, generalize it so that it is a nicer object to work with. I will define the sphere data. So let me now motivate this by considering the case now that we are doing measurements somewhere here. We put a point source here, and there would be 3 scatterers here. The wave starts from this point source. It starts to propagate. Now it hits. And this moment, when it hits to the scatterer, this scatterer becomes a new point source that sends a signal. These propagate. Then they hit to the next scatterer. This becomes a new point source, one more, and in this way the waves propagate. And here I use only single scattering, so waves, only the incoming wave scatters, and there are no multiple scatterings. And let's assume that we now know we measure things here on the on the left side of this line here, or some subset of it. For instance, let's assume that we measure the waves in this area. So let me once run this again. Okay, waves come and produce. Oops, sorry. Let me go this. And this is how we record the data. Let me now look at the time moment when the reflected waves came to this point. At this moment, the wave fronts look like this. So there are this type of curved wave fronts that are recorded, and these are these different times. And the time when we observe this type of wave front, it is now here coded with different colors. So I draw this type of circles or arcs of circles. They are coded by color, and color tells what is the time when they were recorded. So now I do measurements only on a portion of space-time, portion of space. So data from these scatterers at this point looks like this. If one of the scatterers goes very far away and there is varying speed of waves in this area, the wave fronts can be more complicated. There appear this type of like caustic points, and they are difficult to deal when you are analyzing the measurements. And they come from the fact now that there is conjugate points, or there are like multiple like waves. There are multiple roads that the wave can travel. So let us now start mathematical definitions. When I have point y, I will consider generalized spheres that have this center. So sigma here is a subset of generalized sphere. Generalized sphere is all geodesics starting at point y to direction xi, when xi runs over all vectors having length 1, and they run time t. When t is small, the sphere usually is close to Euclidean sphere. Then when t comes larger, we look larger sphere in the travel time metric. So now we are considered that the travel time between 2 points gives the metric, or actually the distance between 2 points. So, and there is a Riemannian metric that is associated to this travel time distance. So distances are actually travel times, and there is a Riemannian metric that is related to propagation of the speed of wave propagation. So when t is small, sphere looks like this. With larger t, it can look like this, and now when t comes even larger, the sphere can look like this. So I call it generalized spheres because so I consider this whole surface. This is where geophysicists could think that they observe wavefronts. Let me now define the sphere data. The sphere data consists of a subset U, open somehow for a small ball in space, and we assume that we know this set, and we know all pairs sigma and t, where sigma is a smooth subset of a generalized sphere. Some open part of it. We consider all subsets. Let's go back to this general sphere. So here is like one piece that is here. Then there's other piece here, and also I could take here smaller portions. We are taking only this kind of smooth subsets of these general spheres, because analyzing measurements close to the caustic points is difficult. So these are open subsets of spheres. This is the radius of the sphere, and the sphere has somewhere here, it has center point, but those are unknown. So the sphere data is just collection of all spherical sets, these type of sets, in this domain, and with the radius of these spheres. So this could be the idealization of somehow, like after a little bit manipulation of this type of measurement data. When we somehow now look the surfaces, we could also take their maximum component in this U. Yeah, so equivalent definition would be that
this is highly redundant, right? You can go this and then this and this, this.
That's true. Yes, there are these maximum components. Then we could. This equivalent data would be to say that we take maximal smooth components of spheres in this set. So our result is that when we have a complete or compact two-dimensional manifold, you could also think Euclidean space with varying wave speed, and we have some open set where we know all sphere. We know the sphere data, that is all pairs, open subsets of spheres, and the radiuses of these spheres. Then we can reconstruct the universal covering of the manifold and the metric up to an isometry. And then one could also build up an example. For instance, consider a torus, a periodic square, and the whole R2, and the data, when you somehow consider the data measured in sufficiently small set, that would be the same. So in this sense, this result is optimal. Actually, what we are going to do, we are going to look basically to how these spheres are curved, and we are going to use like this data, and we can do also this kind of local construction where we somehow are reconstructing the wave speed close to one ray. So that we have all pairs of all the surfaces and all these. Yes. So the data looks like this. You could take these like maximal open smooth subsets if you want, and they correspond to some center that is unknown, but the color here tells what is the distance to the center. This was related to the earlier work that we did with Kurilev and Ullman, where one considers broken geodesics, where you send geodesic to the manifold from one point to some direction. It goes in, scatters somewhere, you don't know where, comes out, and you record these arrows, the positions where the geodesic goes out and goes in, their directions, and also the total length, the length that this geodesic totally has. And in this case, one could consider the manifold up to an isometry. So this type of data related to broken geodesics would correspond to marked sphere data, where when we have like different components, smooth components, possibly for these kind of wavefronts that come from different directions, we would know that they come from the same point source, so there will be more data, and it also requires some additional data near caustics. And this result could be applied to radiative transfer equation when the velocity of waves, c of x, is varying. But this result had the proof that the proof that was somehow quite abstract, and it was very hard to turn to an algorithm that one could use in practice. So with this geophysicists, we started to consider this sphere data problem, and so that it has quite constructive solution along a geodesic by solving just as a system of ordinary differential equations. So first, when we started to work with in this geophysical problem, there was a huge mixture of what somehow, when one looked at these curves here and says that okay, you are measuring the curvature of these wavefronts, then the problem is what are these curvatures? And now in mathematical literature, there are different type of like curvatures that I want to now separate. So when we consider a travel time metric, GJK, this is how I do everything now in two-dimensional case for simplicity. So there's curvature tensor of the space that is measuring how much the space is curved. Then when I have the surface sigma in the space, then I can measure how much this surface or this curve is curved in the manifold that it has also that is curved itself. So R is the curvature related to how the space is curved, and then we speak about the second fundamental form of this curve sigma. So if I consider in this kind of picture, this in Euclidean space, if we have this type of curve, the best fitting circle would have radius a, then the second fundamental form would be 2 times this radius a in two-dimensional case. Okay. So now actually the idea is to do the reconstruction by just combining 3 equations in different ways, and they are all are on this equation, on this slide. So let us consider polar coordinates. The space can be curved now. So I put origin here, and I look the polar coordinates. So distance from this point, and then basically like angular variables. Now the angular vector fields here, these red vector fields here, they are called Jacobi fields, and they satisfy this type of second order equation, Jacobi equation here. R here is the curvature. If you would be flat space, like Euclidean space, then this would be 0. And this is the normal curvature in this radial direction. Then we can ask that how the spheres are curved at each point. That's measured. So we have these spheres, and we are measuring how they are curved in the space. So I have S of R is at this point having distance x, it's distance r from the origin, It's the second fundamental form of this sphere. And now Jacobi fields and second fundamental form satisfy this equation. And also this second fundamental form satisfies this type of Riccati equation. So this is just a derivative in the radial direction that is normal towards spheres. Actually, this is when you if you think layer stripping methods used often in inverse problems, you can recognize that actually you could think that this S of R is a kind of like Dirichlet-Neumann like operator for this Schrödinger operator, and this Dirichlet-Neumann operator satisfies Riccati equation. And now, if I want to write the metric tensor into normal coordinates associated to this center, they are given by the inner products of these Jacobi fields. So those I want to reconstruct. But basically I will somehow look these three equations and combine them in different ways to obtain a reconstruction algorithm. The idea will be that I will consider here one geodesic, and for here would be different this kind of center points that I use for the polar coordinates, and I would reconstruct the metric tensor in different polar coordinate neighborhoods related to this center and so on. And they all, these coordinate neighborhoods, they cover this geodesic here, and then I would be able to reconstruct the manifold in this area. So I will reconstruct the wave speed close to some ray. Okay, let me draw a picture that shows the objects we use here. So now we are actually doing reconstruction only along one geodesic. So I take a point X here in the known area where I have on my data. I take a direction, eta, and then I look at the geodesic of the ray going to this direction. So here I put your coordinate parameter on this ray, r, that is just distance from this point X. Then I go to distance t. So here is yt, that is gamma. Gamma is this geodesic, x, eta, that goes to this direction. I go to point gamma t. So I go to distance t along this geodesic. And then I look here spheres. I look point sphere that goes through the point gamma of r. So here is a sphere. This radius here is now, it is t minus r. And this sigma rt or tr, rt, this is this circle or sphere having center gamma t and radius t minus r. So here it hits this, intersects this geodesic at point gamma of r. And at this point there is a second fundamental form, st of r. And now I want to get the equations for this along the geodesic. See. Oh, one more thing. I put the frame of orthogonal vectors here, f1, f2, and this frame moves along this geodesic, and I represent all objects in this frame of vectors.
You use parallel transform, right?
Sorry?
Using parallel transform.
That's parallel translation of this. So it is the second fundamental forms related to the spheres that I want to use. And these, for geophysical language, they are somehow related to this curvature of these wavefronts. So I want to find an equation that explains the curvatures on these curves in my data. Okay. So like I said, I represent everything with matrices using single frame. So I have this frame that is parallel frame along a geodesic. Then we have the curvature of the space at point is gamma r, this operator, and it corresponds to a matrix R capital along this geodesic. And the second fundamental form at this point associated to the sphere that has center at gamma of t is like this. So this is typical representation how we represent these operators in these frames. So now I actually have I want to consider just matrices along a geodesic. So how about the sphere data? The data that I was given, all these pieces of spheres. I can there compute the second fundamental forms of these spheres, and this gives me this second fundamental form or shape operators. So these were like matrices. I can find these matrices when R is 0, and T varies. So this tells what is the center point. I can reconstruct, so my data gives me how much the spheres having center at distance, having center at point gamma of t, how much they are curved. And so sphere data gives, like I said, these matrices at this point. Now I want to propagate them along the geodesic. No, I recall one of these equations of fundamental equations of Riemannian geometry. It is that the shape operators, or the second fundamental forms, they satisfy Riccati equation along the geodesic. Here is a curvature that is unknown. That's like bad news. If I would know the curvature, then I would somehow be able to solve this matrix S of t. But I don't know it. So let's try to find out it. What we do first, I look the inverse of instead of this equation, I look its inverse. So if I substitute k is now inverse of S, I substitute it to this equation and I get this type of nonlinear ordinary differential equation for k. Then what happens when I look very, very small spheres? Spheres with very small radius. Space, when I look at in very, very small scales, looks like almost like Euclidean space, or it actually more probably it looks like a space with constant curvature. So when I look to asymptotics of this, so the second fundamental form, its inverse when r goes to t. So when the radius of the sphere, this radius t minus r goes to 0, where I look very small spheres, I can compute asymptotics, and it looks like this. There's this type of term, and then there is a term that depends only on the curvature, and then some small corrections. This means that the curvature, that is the difficult term, it can be computed as the third derivative of this K matrix when R is T. Now I have this one extra equation that I want to use. So what we do, this is maybe the most technical slide. I take this Riccati equation for Riccati type equation for inverse of S. S was the second fundamental form. I differentiate it many times. So here was the equation. So I do this type of notation. Vj is the jth derivative with respect of t of this K matrix. So here is just the equation. When I compute first derivative, I get this. Then I compute second derivative, I get this. Third derivative gives me this. And this R matrix that is unknown appears everywhere here. But now I have this formula for the curvature. So this object here, when I evaluate it with R and T is the same, that gives me the curvature. Oh, sorry, here should be maybe 1/2 that is missing. So what we do, we got in this R and T plane, here is R variable, Here is t variable. Here is this r is t line. Then t is not large enough. Here is t0. Here, these differential equations are written in this area. So this t0 is that we don't go, we are before first conjugate point of the geodesic. So I get on these segments, I get ordinary differential equations. And here, at the diagonal r is t, I get this unknown matrix R. So this is now closed system of ordinary differential equations in this triangle. And we can solve it, for instance, using Picard iteration. This means that we can find the curvature matrix, representation of the curvature of the space along this geodesic until I go to the first conjugate point where this system has a blow up. So now I have reconstructed a very important quantity how the curvature looks along a geodesic. Now I can go back to the other fundamental equations of Riemannian geometry. So when I look Jacobi fields, that one is at t is r. This is the angular vectors related to the polar coordinates centered at point gamma t. Then they satisfy this equation here, and they satisfy this Jacobi equation. Okay, so now I have given these matrices when, for instance, r is 0. I can compute, I can find this type of Jacobi fields. I take I guess this, I compute what is the derivative of this type of vector field. I get initial data for the second order equation. I solve it. So I can find the Jacobi fields along this geodesic. And then I go back to this equation and find from here what are these ST operators. So what this means? This means that when I have reconstructed the curvature R on segment, I can move my data along this geodesic. So when I have done the reconstruction in this area of the curvature matrix, then I can start to propagate data, how the data would have been like if I wouldn't have done the measurements here at r is 0, but I have done measurements here at this point r is t0. So I can propagate my data along the geodesic and do reconstructions along the geodesic. Now we can present this type of numerical algorithm where in this type of domain in this RT plane. So here we first use this this third order system of differential equations to solve R, the curvature matrix. Then I use to find the second fundamental form in this area. So I basically I propagate the data and the Jacobi fields to this area. Then I start again here as if I would have done measurements here and continue. In this way I march along the geodesic forward more and more. So other way of looking at this is that if you consider, let's think that here would be boundary of some sphere. You could also think that this is the, okay, here is the boundary of some sphere. I consider the generalized normal coordinates having center at this point. And so this is like normal coordinates. And use this point here as an angular variable. So basically these are this type of coordinates where I say that I take point here and go to the normal direction deeper and deeper like this. With the previous construction where I also reconstructed the Jacobi fields, so I can construct different Jacobi fields, GL, the local coordinates of them, along these geodesics. And now the inner products of these Jacobi fields give me the metric tensor. So in these coordinates, we can find the metric tensor. So the moral of this is that I can put here, take one spherical surface and reconstruct in these coordinates the metric tensor. Now when I have this type of one geodesic that is very, very long, it may have many conjugate points. Conjugate points actually means caustics in terms of geophysics or ray optics. I can cover this geodesic with coordinate neighborhoods related to many center points of the polar coordinates. And I can reconstruct the metric tensor in this union of these. So this means that, for instance, I can reconstruct along with this one geodesic in the Fermi coordinates in its tubular neighborhood the metric tensor. Now when I can reconstruct the metric tensor in neighborhood of any geodesic, then one can use some like global arguments, for instance, type of like O'Neill's gluing constructions to reconstruct the universal covering of the metric space. So how about applications? So if we would not have very somehow general anisotropic wave speed, but we would have just a scalar wave speed in Euclidean space, then it is actually possible to do this reconstruction. First, to do the reconstruction in the in this kind of abstract coordinates along geodesics, and then find what are the actual roads in the physical space of these geodesics. So in this way, one could construct the wave speed in physical coordinates along a single ray. And also, when the manifold is reconstructed, even if this is not true, but in general, when the manifold is reconstructed, one can always compute, for instance, the conformal curvature tensor. And this kind of tensor vanishes if the space is locally conformal to Euclidean space. And so this is actually a way to measure is the structure, for instance, in the deep Earth, is it anisotropic or not. Actually, sorry, it's not if and only if result, but it is result that if the conformal curvature tensor is non-vanishing, so it's non-zero, then you know that the metric is not of this type. So that you can detect sometimes if you can see from your data that there must be anisotropy. Why this is so interesting from the point of view of geophysics? It is that, so this is the cross-section of Earth. Here at the mantle boundary, the very end of where the outer core and mantle meet, there's a layer that is not very well known what it is about. But there is a hypothesis that there are some anisotropic crystals in this area. So if one could reconstruct the conformal curvature tensor in this area and sees that it is non-zero, then it means that the metric is there anisotropic. So then this would verify the geophysical like assumption, or this kind of guess, at least with somehow like high confidence that this area would consist of a certain kind of crystals. And that is really important for the understanding of the heat flow from the deep to surface areas of Earth. So that was somehow the motivation of this study. Thank you very much.
It looks to me that this is some sort of differential geometric form of the layer stripping or invariant embedding idea that was being used previously. Do you have any comments on that?
Yes, that might be the case. That there are lots of similarities. Is that when some layer stripping is usually done for this kind of direct noise mapping, and then the and if I understand correctly, in the let me go. Yeah, so this equation is very much like layer stripping equation, and usually that is done for direct noise mappings. And then somehow, if I have understood all correctly, please correct me if I'm wrong, the rigorous analysis for layer stripping methods for direct noise mappings, it's not really complete. And this might be the case because so that it's difficult to analyze the operator equation. This, in some sense, is similar type of analysis for the principal symbols, maybe of this. I'm not sure about that, but yeah.
But if you take the wave impedance and you propagate it, it has this Riccati equation exactly, and so that's known in invariant embedding literature. So there is much more than just layer stripping. So
yeah, that might. I don't know this area so well, but I think that the question in this type of layer stripping methods is that somehow how to estimate when you have it propagated to some depth, how to estimate this term that is here, how to somehow obtain it, and here this is for the scalar equation that makes it somehow easy, because all these objects are finite dimensional, like matrices along geodesic.
well, wave impedance is scalar, so.
Yeah, okay, maybe this has relations to that.
Other questions? I can ask it. Marty, can you return to the part where you recovered this S of R in the direction of the geodesic, and for up to the first
First
point and what before, and that. So now you say you take some other point, right?
And yes, next we first propagate the data deeper.
The data.
So when we I know I have we start with we have this ST at point 0.
But now T is more.
When T is somehow larger than 0, and now we propagate this
larger than 0 or larger than T0.
So this is our original data.
Yes.
And then we will do the propagation so that we actually propagate up to the first conjugate point, and after that
corresponding to T more than T0.
We are doing reconstruction in T from 0 to D0.
Yes. Okay.
And T0 is smaller than the first conjugate distance, and then after that we reconstruct this type of data. And then we march here one step deeper, reconstruct data at this level, and go in this way.
Okay, thank you. Other questions? Thank you again very much.